those two. Okay, and also do 12. Those three are recent problems. 12, I kind of cleaned it up a little to make it a little more straightforward. So you probably want to look at the one on the board now. So it's the same question, but a product review. Do those three. It is a learning experience, so talk it over if you have questions. That would be wise. With those three, feel free to work on something on another problem until we go over it. That's true. Need help getting started, let me know. What are we trying to announce on this? So that's what we should be doing, calculus, what's the area of the so the base, what is it? In terms of x's and y's. 2x. So it's 2 x's and 2 y. So the area is 2x times 2y and 4xy.
It's 2x.
2y to the height, right? That's the area. That's what we're trying to estimate. The circle comes in as a substitution to get it down to 2. Well, that's how you use the circle. Yeah.
Oh, it's full circle.
So,
Yeah.
an organization called
Problem. His answer to the problem.
area direction.
Well, that's a even number anyway.
Fight the conclusion to make happiness.
So-
That's kind of
Not itself. You can't make
That shows the area.
sense.
What's the area? Yeah. In terms of x's and y's. If you go right to the origin, that's x, but you're going right hand, that's the
Oh, you're not gonna put the line next to it, right?
2y.
Zero to the height.
So the origin is 4x. So then what we we're trying to maximize that. So we want to go
Wait, you're 2 over 2?
Why not just go bring it out the grid? If you keep the grid, it's one on the right side, so it's pretty easier. Area is 4xy, right? And you want to maximize area. So you want to know a prime goes back to me. That's maximum. Well, the problem is that there's an x and y. So we sub in. That's what the circle is, right? You use the circle. So it's just that. The optimization ones are tough, so I'm not asking for you to kill a hard one tomorrow, just to do a straightforward one. That which you, oh, I see. If you agree that I could draw a rectangle with up to here, yeah? What's the base of that rectangle? Yeah, if this is 2, then what's the base? 4. So you're saying the base is not x, it's 2x. Okay, and the height is not y, but 2y. So the area should be 4xy, not xy. Yeah. So that means then, now that shouldn't change things considerably, because you'll just have a coefficient of 4 there. Actually, you got 4 up front, you probably will. So, that said, you should. Oh, true. So the top is 18 minus 2x squared. So the quadrant, so you have a quadratic. And that should be your critical.
So,
Did you get a quadratic or not?
Yeah.
As long as you give me some calculus. Yes. Okay, all right, did you talk it over? Have you had enough time to give it a good go? Okay, so the first one, hopefully that went well. What is u? X squared plus x plus 1. Therefore, du is 2x plus 1 dx. If you didn't write that in, write it in. That's the dx matters. Okay, you can't substitute in with du if there is no dx. Those are the little things that students think, oh, that's no big deal. I like that. I'm grading your paper. I think it's a big deal. Okay, so if you don't have that, you best start to focus on the details a little more. They're important. All right. Now, with that substitution, if I substitute what I have, this whole thing becomes du. The 2 is still there, the root is still there, and u. The 2, did you pull it out front or leave it in? I don't really care. Out front. All right, so 1/2 u to the negative 1/2 du gets integrated. What's the antiderivative of u to the negative 1/2? 2u to the 1/2 plus c. And there you knock out the 2's, substitute back in. You could keep it to the 1/2 power, I don't care. You could write it as a root either way. But your final answer should be that or its equivalent. How did it go? Okay. This, you've got product rule with ugly chains within. It's crucial that you keep it organized in deed and thought. So first stays the same, e to the 2x. Boom. Now I work on the derivative of tangent squared, or tangent of x squared is how I picture it in my mind. How do you take the derivative of that? Chain rule. What's the outside? The square. So 2 comes down, drops to the 1, the inside stays the same. Times the derivative of the inside. What's the derivative of the inside? Secant squared. Don't forget where you are in the whole problem. We're doing the product rule. First stays the same, derivative of the second. Now we go to second stays the same, derivative of the first. Derivative of the first, that's a function within a function, so chain rule. Derivative of the outside, e to the 2x times the derivative of the inside. You have that. That's success? Pretty good? All right then. This, the base is 2x. Actually, let's go here. I saw several students start there, and that's cool, but then I had more than a handful take derivative on it. Okay? You're just kind of throwing calculus at it, okay? Remember have clarity of thought, basically. What are you trying to do? Maximize the area of the rectangle. Taking the derivative on that gives you absolutely nothing. It has no meaning to this problem. Nothing. It does nothing for you. Okay? When you get an optimization problem, the first thing you do is say, what am I trying to do? I mean, you cannot do a problem if you don't know what you're trying to do. You're trying to maximize the area. Ask yourself, what am I trying to do? Then you say, what is an equation for what I'm trying to do? An equation is xy is good, but it's really 4xy. Okay. Now, believe it or not, the critical numbers, you'll get the critical numbers right either way, whether you have that 4 or not, but your area at the end would be wrong if you didn't have that 4. So, it's 4xy. Great. So, am I ready to maximize the area and find where a prime goes positive to negative? Yeah, that's going to be kind of ugly. What's wrong with that? 3 variables, okay? So you try and get it down to 2. That's where the circle comes in. The circle is just a supplementary fact. It's not the star of the show. If x squared plus y squared equals 9, then you might say y is the square root of 9 minus x squared. So the area is 4x root 9 minus x squared. Now I have it down to two variables. Now I can find where a prime goes positive to negative because that's a math. Here goes some ugly calculus. Is it a dA dt? No, there's no time component to this. It's not changing with time. As I choose, again, just shooting for total understanding, it's as I choose different x's, I get different areas. So I'm looking at how does the area change as I change x. If I keep stretching x out, the area will get bigger and bigger up to a point, and then it'll start to get smaller and smaller. You see what I mean? If I drew a rectangle like this, I'd have small area, bigger area, but at some point the area is going to start to get smaller, and I want to know when did area stop increasing and start decreasing, and so I'm looking at how a prime behaves, the change in area behaves. When did the area stop increasing and decreasing? So, now let's talk derivative. Did you do the derivative successfully? First stays the same. Derivative of the second is 1 over 2 root 9 minus x squared times the derivative of the inside, negative 2x. We? Plus, second stays the same, times the derivative of the first, which is 4. We need to know whether this is 0 or undefined for critical numbers. All right, now here's the problem, the part that students start to make mistakes on if they got this far. That algebra is important. The common denominator, let's hack out of 2, shall we? What's the common denominator? Root of 9 minus x squared, okay? This guy you didn't have to do anything to, so what's the numerator on this one? Negative 4x. Wait. This, oh, sorry, not 4x. What's wrong with that? I circled wrong. 4x squared, sorry. Negative 4x squared. What did you multiply this by top and bottom to get the common denominator? Root of 9 minus x squared. So this becomes 4 times regular 9 minus x squared, or 36 minus 4x squared. Do you see where I'm coming from? Okay, now what? Here's where you participate in your education instead of just waiting for me to do everything for you, which gives you nothing. Combine like terms. Yeah? Solve it. How do you solve it? Undefined if bottom is 0. So that would be plus or minus 3. That would imply that the rectangle is sitting right on the x-axis. That's a minimum area. That's not a good thing. Okay? Now, this equals 0. And by this, I mean a prime equals 0 if the numerator equals 0, right? That's at x equal 36 over 8 square rooted, or take a 4 out, maybe 9/2 square rooted, and that's fine with me if you leave it like that. Okay? Last but not least, make sure you answer the question. What does the question ask you to find? The way I wrote it in the top. What is the maximum area of the rectangle? Did I find that yet? I did not. So I need the area. How do I find the area? I have this magical x. Yeah. Plug it in. Here's the best place to go because that's the area of x only. So 4 root 9/2 root 9 minus root 9/2 squared. That I don't really care about, but that inside is just ugly. What is that all coming out to be? 9 minus square root of 9/2 squared is just 9/2. What's 9 minus 9/2? 9/2. What's root 9/2 times root 9/2? 9/2. So what's the max area? 18 for you. Okay. Now, if they asked for instead for dimensions of the max rectangle, then you would be finding x and y and expressing the base as 2x's and the height is 2y. Okay, those are tough, but you've got to start to make headway, okay? The calculus is ugly and you have to be good with details. All right, speaking of calculus, let's talk huge, and I'm talking huge ideas of calculus. Are you ready? Darn it, never mind. There we go. Cool. Okay, so here's the thing. Set 55 in the book is Maclaurin series. Series are part of calculus too. I have no idea why he chose to put them in at that point. It's not a good point to put them in. And so I will be replacing those because that's just a So I will be talking about a big idea of calculus. Fundamental theorem of calculus, part 2. But we'll get there. First, these are big idea problems, definitely represented on the calc test, so please ask questions as you go. If you're not with me, then say so. Check that out. This is kind of a weird integral, in that it's got an x in the upper limit of integration, yay? That is sometimes called an integral defined function. I will explain that in a minute, but let's just start with what it is. If you were to integrate, and when we do a definite integral, we integrate first. What's the antiderivative of cosine u? Sine u. And then you integrate at the upper, or you evaluate at the upper minus the lower. So I would put x in and 1 in, yeah? So at the end of the day, that integral would be sine of x minus sine of 1. A bit of vocabulary. That u there, that's called the dummy variable. It's just kind of holding the place. The end result, the answer to this was actually a function of x. Final answer is depending on x, not u. Because x goes in, is substitute in at the end. The u kind of does its job, holds the place, but it doesn't show up in the final answer. It's a dummy variable. So say you looked at this one. This function, what's the dummy variable? T. T is the dummy variable, just kind of holding the place until you integrate and substitute in. When integrated, after it's all done, the function will be a function of x. This is actually a function of x. Despite the fact you see t's in the integral, it's actually a function of x. Now, this right now is a whole bunch of symbol fish. With a graph, you'll start to see what this actually means. If I showed the meaning of f graphically, then I know an integral is area under a curve. In this case, it's the curve 1/2 t plus 1. If I were to graph that, I know it's a line with a y-intercept of 1 and a slope of up 1 over 2, up 1 over 2. So far, so good. Now, it's, as I said, f is the area under the curve starting at 1 and area from 1 up to where? Where? X. Now, x could be anywhere here. X could actually be here, or here, or here. X is a variable for a reason. It's the area. Depending on where you end the region, you get different amounts of area. So F is the area under the curve. You could think of it, and it's frequently called F is an area accumulation function. How much area would be dependent on where you ended the region. If the bigger the x, the more area you accumulate. You with me so far? All right then. So f is an area accumulation function. Let's then look at this in a common AP kind of problem. I am giving you that this is the graph, some graph of f of x, okay? G of x is an area under f function. It's defined, an integral defined function. It's defined as the area under the f curve from -3 up to some point. If I ask you for g of 0, start by just good function basics. Put 0 in. G of 0 is that. That means x is 0. I put in 0 in place of the x, and that's what I get. Now, if I'm to then actually get a numerical answer, I need to figure out what is this integral equal to. Well, integrals represent area under the curve. On such a problem, it's not expected that you write the equation of this, x squared plus y squared equals 9, and integrate. That's not the idea. The idea is that you find the area geometrically. If I want the area under f, I could say, well, that's a quarter of a circle with a radius of 3. And so g of 0 is the area under the curve, and that is 9 pi over 4. Would you then try, oops, this is not g of 3, this is supposed to be g of 1.5 or 3 halves, and g of 3. Okay, so g of 3 halves. That's the area accumulated from -3 up to 0 under the curve. Not to 0, dummy, sorry. From -3 up to where? 3 halves. Okay. So I need to calculate the total area accumulated under the function. Well, I know the semicircle, I already have that done. It's 9 pi over 4. I just need to add in the triangle I just tacked on to the area. What's the base of the triangle? 3 halves. What's the height of the triangle? 3 divided by 2. And so g at 3 halves would be something like 9 pi over 4 plus 9 over 4. Nope, that's, yeah, 9 over 4. Yeah? Very cool? Do you agree?
Yeah.
Okay. Now, last thing, as you can see down here, if a region is below the axis, if I look at this region here, these y values, imagine rectangles here, those y values are negative. And if I take a base that's, if I go left to right, the delta x is positive, but the heights are negative, then this area is going to be negative. And so when you go to find g of 3 and say it's going to be 9 pi over 4 plus 9/4, what I had before, and then I tack on that extra area, that area will be negative because the y values are negative. I know that kicks students out, negative area, but because often in calculus we want negative change, the negative is okay. What's the base of that and the height of that? It might look similar. It is the same, so 9/4. So what is g of 3? 9 pi over 4. That positive area is the same as the negative area, so those two knock each other out, and you get that 9 pi over 4 semicircle. Questions so far? Okay. Let's go at this a little differently. Okay, working still with integral defined functions. Say you had that original function we talked about a second ago. F of x is the area under the line curve. And we want to find f prime. Now there's a shortcut to this, but let's go with the long one. if I wanted to find f prime, then that really means I want to take the derivative of that thing. I can't take the derivative of that thing until I know what that thing is, yeah? So we're going to work the inside. We're going to integrate first. What's the antiderivative of 1/2 t? 1/4 t to the second or squared. And what's the antiderivative of 1? T. And I need to evaluate that from 0 to x, yeah? I have not taken the derivative yet. Keep it there. If I evaluate that at x, then x goes in for every t, and I get 1/4 x to the second plus x. And the 0, or the, 0, this should be 1, should it not? This, I typoed here, that should be a 1, and this should be a 1. If you put in a 1, you get out 1/4 plus 1. All right. Now I could then anti-differentiate. I could clean up inside, but I don't need to because now I'm going to take the derivative of the inside. If I take the derivative of the inside, what's the derivative of 1/4 x squared? 1/2 x. What's the derivative of x? 1. And what's the derivative of all this constant stuff? 0. Okay? Well, then you can see basically what you probably saw coming all along, and that is that if you take the derivative of the antiderivative, they totally cancel out, and you're right back to where you started. The only difference is the dummy variable gets subbed for the actual variable along the way. And so the fundamental theorem of calculus is just the derivative of the antiderivative is the function. They undo each other. There's a chain rule part to this that we could get at later, but for now, let's just keep it straightforward. So in the function above where I said g of x is, I need to copy something real quick, sorry, just a second. Okay, I need this graph. Okay, sorry. Oops, that's something a little marked up here. Okay, so in this problem, we said g of x is the area under f from 0 to, or -3 to some point, yeah? Are you with me? Okay, so g prime at 0 would be the derivative of the antiderivative, and therefore just the function. So g prime of 0 is actually equal to f at 0. The derivative of the antiderivative is just the function. What is f at 0 according to the graph? 3. See? Here's the f graph at 0. The graph is at 3. What is g prime at 3? G prime at 3 is equivalent to f of 3, because the derivative of the antiderivative is just the function. F at 3, according to the graph, is -3. And I don't know what g prime at 6 is. That's crazy talk. Let's go g prime at 3 halves. What is g prime at 3 halves? F at 3 halves, which is 0. Okay? Well then, if g prime is equal to f, then g double is probably equal to f prime. G double at 0 is equal to f prime of 0. Now that's the slope at 0 of the f graph, and the slope of 0 at the f graph does not exist. It's undefined because there's a sharp turn. Wait. So it does not exist or undefined. What about g double at 3? Always state what it's equivalent to in terms of what you're given. You're not given G double. If you give me an answer here, you're making an inference, not communicating what it was. So you need to express how you're getting your answer. G double at 3 is equivalent to F prime at 3. F prime at 3 is -2. How'd you get that? The slope. That's the slope. So F prime at 3 is -2. G double at 1. G double at 1 is also F prime at 1, which is -2. Okay. You with me? All right. These are very common AP style questions. We'll practice them as we go. All right. Now, switching gears slightly. Calculus part 2. As applied to change, accumulation of change. Some books might call this total change word problems or net change word problems. But gosh, this is some of the coolest stuff in practice. If you integrate a rate of change, you're getting an amount of change. I will explain in a second here. Say I gave you that the number of people in the store at some time is changing at a rate of R of t, where t is in hours since the store opened and R is in people per hour. If you did this kind of integral, then in terms of units, R's units are people per hour as far as how the number of people in the store are changing, right? What are the units on dx? That's actually a time, but that's times hours. So when you make this little rate times time calculation, it's actually change in people, change in number of people in the store. What about the limits of integration? Change in the number of people in the store when? Change in the number of people in the store from time 0, when it opened, up to what point? Any time t. Now, that's change. It's crucial that you see that integral as the change in the number of people, not the number of people. To know the number of people, it wouldn't be enough to just know how much it changed. You'd also need to know how much it started at. Okay, you need to know how much it started at, how much it changed, to see how much was there later, right? So to find the number of people in the store at any time, you would need how many people, number of people at the start. And then add the change. So an initial condition plus the change gives you an ending point. For example, you might say n of t is the number of people at the start plus the change in the number of people up to some point. What is x? X is the dummy variable. It's just holding the place until you integrate and put in t. So the number of function would depend on how long you've changed up to. Okay, so the ending result would be a function of t. This we could do in a velocity case, and then we'll do others at the bottom of the page if we have time. The velocity of a car is given by that ugly function. That is ugly for a reason. You are not meant to integrate that. Meters per second. At time 0, the car is 3 meters from the reference point. Super. Give an expression involving an integral for the position of the car at any time t, involving an integral. So you're not going to say, I know that position is the antiderivative of velocity, so let me try and figure out how to anti-differentiate that. That's not going to happen. You cannot integrate that. All you can do is make area calculations under the curve. It cannot be integrated. So that's why we do this integral evaluation or integral. To know the position, I would need a starting position plus what? Starting position plus change in position. How do I find change in position? An integral of v, yeah? V of t? Okay, is it okay to say this? What about the limits of it? Let's say it is. The limits of integration from when to when? 0, starting at 0 up to some point t. Can I use t in two totally different fashions? Hey, t is going to make the curve, so it's all points, but also t is specifically the endpoint. Is that okay to use a variable in two ways? No, it's not. And that's why you use a dummy variable. You must hold the place by using something. You could use u here. You could not use x because I have x using for the function, the position itself, but use some variable like u or something that's not in the problem already. You with me? Okay? So if I wanted to find the expression or the position at time 17 seconds, I could say x at 17 is the starting position. It started at 3 meters from the reference point, and throw in 3 for the upper limit of integration, right? What is this finding? Change in position, and you're tacking it on to where it started. Start plus change equals ending position. With me? Okay. This I threw in later. This is not really part of the idea. We'll talk about that tomorrow. Don't worry about that. All right. I was hoping we'd have time to get to the mosquito problem.
Mr. Rico,
Yes,
I went to 3 instead of 17.
because I'm an idiot. Sorry, I was thinking of something else. Because I'm dumb. I got lucky. It should be no rough day. 17. You're correct. It is. It should be 17. Thank you. That's why it went silent all of a sudden. Okay, that's correct. Okay. That is pretty decent. Actually, we might as well. We got 4 minutes. We might as well tack this on. How would I find out? Go ahead and get your calculator out, please. Maybe we can crank this one out. This, I think, is a good problem. How do I find out how far the car goes backwards on 0 to 2? How would I do that? I know it's velocity. How do I find distance or change in position or something? What do I got to do? Let's start with one of the two. Calculus is 2 ideas. Derivative or integral. Which one? Integral. You're going to integrate velocity to get change in position, right? Rate times time. What else do we need to consider? The what? Yeah, the negative. I need to find out, what about the negative? I don't know when it's moving negative. Don't I need to find when it's moving backwards? What am I going to do to find when it's moving backwards? You could do a sign test. You could, if I were doing this analytically, that is exactly what I would do. Graphically, because I have a graphic calculator and that function is stinking hideous, what else could I do with my calculator? I could graph it and look at where the graph is below the axis on 0 to 2. I would definitely set my window to 0 to 2. Zero to 2. I hope it doesn't go too much. Oh, baby. Oh, no. Oh, boy. All right. That's bad. Oh, man. My bad. Do you have the graph yet? Okay. So here's the problem. Poorly designed. I should have known this was going to go hardcore oscillation. But on 0 to 2, because this is cubing, it's starting to go through some periods super fast. If a period is constant, then it goes through a period in 2 pi. But because that time is cubed, it's going through its cycles faster and faster and faster. So you're starting to see it go something like this. So unfortunately, that makes for a lot of negative movement situations. I have at least 1, 2, 3, 4 areas of negative movement. That was not my intention that I just inundate you with negative movement. But let's just talk about what we would do had it been maybe 0 to 1.25, which might cut about here. Say I had cut it there. What would you do to answer the question? Find in your calculator, you would find what? The zeros. You would need to know when it started going backwards and stopped going backwards. And once you found those, call them A and B, then what would you do? You'd integrate from A to B and B. What kind of answer would you get there? You'd get a negative one, because it's negative velocities, you'd get negative movement. And so as far as how far backwards, you just say it's that. The absolute value of that for the actual distance you travel. All right. If you've got a good chunk of that done tonight, then you would have less homework on the weekend. And you use that tomorrow we'll get caught up on questions. Make sure you're caught up on everything. And we'll turn in a lot of stuff tomorrow. Have a great day.